The table on the slide illustrates the characteristics of the three application types in Layer 7. The Layer 7 of the OSI model is the application layer. Let us first look at the three types of applications. They are interactive, batch, and real-time. In an interactive application, you enter data and wait for a response. So response time is important but not critical unless the wait becomes excessive. An example of an interactive application is a web search engine. You enter a search term and wait for the results. In a batch application, you enter a command or a string of commands called a batch. You do not wait for a response. Here, bandwidth is important but not critical unless the batch application takes too long to execute. An example of a batch application is file transfer. In a real-time application, there is person-to-person real-time interaction. Here, end-to-end latency is critical. In this context, latency is the time taken for the data to go from the source to the destination. Excessive delay affects the person-to-person interaction. Examples of real-time applications are voice over IP, VoIP, and video conferencing. Let us find out the specific requirements of Layer 7 applications. This can be called performance requirements and is discussed in the next slide. There are many ways to measure the quality of data communications: delay, jitter, and loss tolerant. Delay corresponds to response time. It measures how quickly a response from input is expected. Jitter refers to the variation in delay. An application can respond quickly to one input, but slowly to another if tolerance for jitter is high. For example, a constant delay on a telephone call is not as annoying as a variation in delay or the jitter involved in the call. If an application is loss tolerant, data losses are acceptable. This assumes, in the case of interactive and batch applications, that the data would be retransmitted. In VoIP and video conferencing, the data would just be dropped. The next slide shows the performance requirements for various Layer 7 application types. The table on the slide provides details of different protocols used for file transfer and remote access. For the CCNA exam, you need to know the type, TCP or UDP, and port number of all the protocols. Telnet Protocol, TCP port 23, provides remote access to another device. It uses plain text. Secure Shell, SSH, TCP port 22, allows remote access but provides encryption. For using remote access for Cisco devices, SSH is preferred. File Transfer Protocol, FTP, TCP ports 20 and 21 transfers files. FTP also allows access to both directories and files. Trivial File Transfer Protocol, TFTP, UDP port 69, is a simplified version of FTP. It is extensively used in managing Cisco devices. Hypertext Transfer Protocol, HTTP, TCP UDP port 80 and 8080, manages communications between web browsers and web servers. HTTP running over Transport Layer Security, TLS, Secure Socket Layer SSL, protocol is called HTTPS for HTTP Secure. It uses TCP port 443. Like HTTP, it manages communications between web browsers and web servers, but in a secure manner. Let us move on to discuss the protocols for network services in the next slide. The table on the slide provides details of different protocols used for network services. Simple Network Management Protocol, SNMP, UDP port 161, is a network device manager. Network Time Protocol, NTP, UDP port 123, synchronizes the clocks in a network to one standard source time. Domain Name Service, DNS, TCP UDP port 53, resolves host names. It translates between fully qualified domain names, FQDN, and IP addresses. For example, on entering the FQDN www.google.com on browser, DNS translates that reference to the IP address for that website. A URL is an FQDN along with the protocol, like the one seen on the slide. Dynamic Host Configuration Protocol, DHCP, UDP port 67 for server, 68 for client, assigns IP addresses to devices on the network. Let us move on to the Layer 4 in the OSI model, which is the transport layer. The table on the slide shows the main protocols used at Layer 4, which are TCP and UDP. Data from higher layers are broken into segments for efficient transmission. Transmission Control Protocol, TCP, is connection-oriented. This means it keeps track of a data flow. Once a TCP session is established, it is maintained until the sender or receiver terminates the session, just like a telephone call. TCP keeps track of segments that have matching source and destination port numbers. TCP also provides reliable transport of the segment. If the source does not receive an acknowledgement that the segments have been received at the destination, the source retransmits the segments. User Data Protocol, UDP, on the other hand, does not provide reliable transport. UDP is faster than TCP because acknowledgement is not required. Also, UDP does not keep track of a data flow. It is a connectionless protocol. Now let us look more closely at TCP header in the following slide. A TCP header contains the following fields, among others: source and destination port numbers, sequence number, acknowledgement number, window size, and checksum. Each segment is assigned a sequence number. The sequence numbers are used for two purposes. The first purpose is to determine any segments that require retransmission. The destination uses a sequence number when sending an acknowledgement for the segments received. The second purpose for sequence numbers is to be able to reassemble the segments in order at the destination. Since segments are transmitted separately, they can arrive at the destination at different times. Therefore, they must be reordered. In the next slide, we will understand how TCP starts a session. The image on the slide depicts a three-way handshake, which is the beginning of a TCP connection. The control sequence is as follows. SYN, the source sends the initial sequence number. SYN-ACK, the destination acknowledges the source and says it is ready for the next sequence number. ACK is short for acknowledge or acknowledgement. ACK, the destination tells the source to keep transmitting. Now a TCP session has been established. It will continue until either the source or the destination terminates the session, similar to a telephone call. Next, we will discuss windowing, which is another TCP feature. The image on the slide illustrates flow control or windowing. This is a process used by TCP to control the amount of data sent at once. TCP uses windowing, also called sliding windowing, to determine the number of segments to transmit simultaneously. If there is a large amount of traffic, the window is made smaller. If the bandwidth is available, the window is increased. The next slide deals with the concept of UDP. The table on the slide shows the fields in a UDP header, which is much smaller than a TCP header. It contains only source and destination port numbers, length, and checksum. UDP is a connectionless protocol since UDP's header has no sequence number. It cannot reassemble segments in order at the destination, unlike TCP. UDP is used in two circumstances. The first is when reliable transport is not necessary, for example, when looking up a DNS name. If you send a request to a DNS server and receive no response, you need to try again. It is not important to use acknowledgements in this situation. UDP is also used when the delay introduced by TCP is unacceptable. For example, in Voice over IP, VoIP, it is important to get a segment to the destination as fast as possible. If a few segments are lost along the way, that is acceptable. In fact, if the segments don't show up right away, they are not required. If you insert delayed segments into a voice call, it would jumble the conversation. In the next slide, we will discuss port numbers. The table on the slide shows how the port numbers are assigned. Port numbers are assigned as follows. 0 to 1023 are well-known ports. 1024 to 49151 are registered ports, and 49152 to 65535 contain private or dynamic ports. Both TCP and UDP use port numbers as addresses. Dynamic ports are used to allocate ephemeral ports. These are used as the source ports for Layer 4 communication. Well-known or registered ports are used for destination ports. For example, when you send an HTTPS request, the source port is a dynamic port and the destination port is TCP port number 443. In the next slide, we will understand Layer 3 protocols. Layer 3 adds an Internet Protocol version 4, IPv4, or Internet Protocol version 6, IPv6, source and destination address to the segment received from Layer 4. IP source and destination address are the logical addresses for a device or router interface. This compares to the physical addresses that are used at Layer 2, for example, Media Access Control MAC addresses for Ethernet. Other important protocols at Layer 3 for IPv4 include Internet Control Message Protocol, ICMP, and Address Resolution Protocol, ARP. Let us begin with ARP in the next slide. The image on the slide demonstrates how Address Resolution Protocol, ARP, works. It finds the corresponding MAC address if IP address is provided. ARP is used when forwarding a packet to the correct destination within a LAN. The IP address MAC address combination is stored in the ARP cache for future use. Here is an example of ARP. A PC knows its default gateway as an IP address. To get to its default gateway, however, it uses Layer 2 since the gateway is in the same subnet. Therefore, the PC uses ARP to find the MAC address that corresponds to gateway's IP address. Now let us look into the most important Layer 3 protocol, that is, the Internet Protocol version 4. In the next slide, we will discuss the header of IPv4. The image on the slide shows the different headers of IPv4. IPv4 is the standard Layer 3 application for routing. Some important fields in an IP header are source and destination IP addresses, header length, and differentiated service code point, DSCP, type of service TOS, used for quality of service, QoS. We will continue our discussion of IPv4 in the next slide. The image on the slide demonstrates the time to live, TTL, and bits concerning fragmentation field and function of IPv4. Bits concerning fragmentation. If the number of bytes in the data causes the packet to be too big to send through the network, it is fragmented. This means it is sent in more than one IP packet. Some applications cannot work with fragmented packets. In this case, the Don't Fragment DF bit is set. More fragments MF signal signifies that more parts of the communication are contained in other packets. The time to live TTL field is very important. When a packet arrives at a router, the router decrements the TTL field by 1. When the TTL field becomes 0, the router discards the packet. TTL prevents packets from continuing to look for a non-existent address indefinitely. Without a TTL, there would be many packets taking up bandwidth and processing power running around the Internet. Let us focus on some Layer 2 protocols in the next slide. Ethernet is the primary Layer 2 protocol used on a LAN. Other Layer 2 protocols are Point-to-Point Protocol, PPP, High-Level Data Link Control, HDLC Protocol, Frame Relay, and Cisco Discovery Protocol, CDP. The source and destination addresses assigned at Layer 2 are physical addresses. For example, an Ethernet MAC address is a physical address. It corresponds to the network interface card in the device. Addressing used at Layer 2 is flat. There is no hierarchy involved, as in Layer 3, where IP addresses are part of a network. Visually, the topology is similar to a tree. It starts with one router, followed by two switches and various types of end devices. This is a hierarchical structure. Since Layer 2 addresses have no hierarchy, they are not useful in defining such a structure. In the next slide, let us find out how the layers 7, 4, 3, and 2 interact. The image on the slide shows how the adjacent layers interact. Adjacent layer interactions take place between OSI layers on the same device. Example: the encapsulation of a Layer 2 frame with an IP header including source and destination IP addresses. The datagrams are sent up or down to the next layer in the OSI model. Same layer interactions occur between different devices at the same OSI layer. When routing information is sent from one device to another, the devices communicate with each other using Layer 3 information. When a switch forwards a frame to another switch, both switches are operating at Layer 2. Let us move on to the quiz section to check your understanding of the topics covered in this lesson.